So what we have seen so far is the zeroth and first order corrections to the energy and the eigenstates of our full Hamiltonian, right, with the perturbation W that I wrote before. So again, we have this Hamiltonian, we have computed the first order correction when we consider this. Okay, in terms of a power series in lambda. Well, lambda is just some parameter between 0 and 1. Now, we said that this is the Dirac expression for any k equals or to 1 or greater than 1. So let's just compute the second order correction. And actually just a heads up, from the second order correction to the wave function, you will almost nowhere see it in any place because the expressions get too long and too complicated, and really the first order correction and the second order correction to the energy are more than enough to make really good approximations and understand our physical system. But today what we're going to be doing is to write the second order correction to the energy and second order correction to the eigenstate. And for higher orders, if you want me to do it, I'll do it in other videos just for fun. But for higher orders, we have this relation. We just have to apply the same method that we have been doing now, just multiplying by phi 0 L, for L equals N, and L is not different from L. We'll see it now. Just get your corrections. Again, if you want me to do it, just leave a comment and I'll do higher order terms just for fun. But as I said, you will not see it in many places because calculations are too long and expressions are not too useful. They're too long. But well, let's just do it. So for k equals to 2, we get that our general expression is just h naught second order correction plus let me just write it like this, plus hp times 2 minus 1 is just first order correction, and this is equal to the sum going from 0 to 2. So if we expand it immediately, we get en 0, 2 minus 0 is just 2, plus en 1, 2 minus 1 is just 1, and en 2, sorry, and 2 minus 2 is 0. So this is our equation for the second order correction. And well, we could replace this by the sum and this by the sum again, but we're not going to be doing it just now because we have to write a lot and we can actually work with this really easily. So this is the zeroth order correction, so we do know that this is just phi n 0. What we're going to do, we're just going to take the inner product with L equals to N in this case. Okay? So I will write in general expression here, and then we'll just particularize for L equals N. So what we're doing is taking the inner product with some element of our basis. Let me just write like this. L0 HP first order correction, and here I'm immediately going to use the fact that the inner product is a linear operator. It is linear, and it has the property that we can take the constants out. So we get the zeroth order correction, phi L0 type to n plus en1 phi L0, first order correction, plus en2. And let me just, because this is what we're going to be using, so let me just put this square. Notice that as we increase the orders, we get one more term here. So for third order, we'll have 4 terms. For fourth order, we'll have 5 terms, and so on, so on, so on. So for increasing orders, as I said, this gets a lot more complicated and a lot more arduous to do. But for second order, it's more or less fine to do it. So we derived previously, in the previous video, this expression right here, that we have phi 0L times H naught times some arbitrary element of our Hilbert space. This is just a state, consider the energy of that state and take the inner product. So we can rewrite this as, let me just put this, we'll put it equals to n afterwards. So we can rewrite this as this. Using this property. So let me just rewrite it. Now, in general, we said that Kn is the sum over all m of Cm, and I'm going to write a k here just to indicate that it's coefficient of the kth order correction, times this. Assuming that this is convergent, of course, it's convergent to this one, and that we can take the inner product inside, we will get that if we take the inner product with any correction, well, we can just do this. This, we said before, because it's an orthonormal basis, is just the Kronecker delta. So this is just the delta. This just means that it is 0 when L is not equal to M, because they are orthogonal or orthonormal, and is 1 if they are equal. So L equals to M, we get CLK. So whenever we have this is just the CL component of our correction. So let me just write it like this. C2L. This one is again C2L, and this is C1L. Right? Yes. Let's check. Yes. So that's it. Now, let's choose L equals to N. In this case, we will just get, well, En0 Cn2 plus this, which we cannot simplify any further with, because again we don't know HP. This is just En0, that's the component, the CL component of our second order correction, plus, this would be an N, okay, because we are making L equals to N. En1, the Cn first component, plus, well, these two become just one, so this is it. And this is it. Notice that in general we do need to know Cn1, but we don't know it yet. So for now, we're going to leave it in terms of Cn1. But we'll see later on that, surprise, it is 0. So this term is equal to this one, so they can cancel out, and we get our expression for the energy correction. So En2 is just this. HP1. I'm going to leave some space because we're going to expand this afterwards, and we just subtract the first order of energy correction, Cn1. For now, we'll just leave it in terms of Cn1. I'm going to write it like this, just so you know that we don't know it yet, but we will in the future. So this can be expressed as, well, as the expression we got before, right? This m over m is not equal to n of this. En minus En. Now, we can take this inside the sum, so we need this conversion and everything. And what we would get is the following. If m is not equal to n, then we just get, well, the same expression, 0 hp hn 0 times this inner product. This one, okay, we can just take it in because all of this is just a constant, really. This ends up being a constant, because yeah, we're changing the inner product between two elements of a Hilbert space, and this is another constant. So all of this is just constant. We're gonna take it out and plug in this. Okay, so this would be our second order correction to the energy, and in many places you will see it pretty like this. Here we are assuming that HP is not self-adjoint, but in general it will be self-adjoint because we're assuming that it is a valid Hamiltonian. So if HP dagger is equal to HP, which is the general case, we should be equal to that if we are meeting that H is equal. If the full Hamiltonian is equal to its dagger, then this has to hold, okay? So for it to be a valid Hamiltonian, it has to be self-adjoint, so this has to hold too. So in that case, we can just say, okay, let me just write this first term here. And let me just take the complex conjugate. Then we just have to invert the order, right? Take the dagger here and put this one here. But because HP is equal to HP dagger, we just get this. But this is the same expression of this one. So this is the complex conjugate of this one. And we know that in general, in their numbers, that if we have C times C, the complex conjugate, we just get d modulus squared. So instead of this, we can just write the modulus of this inner product squared, or the modulus of this inner product. Really is just the same, just a complex conjugate. Well, so this would be our expression for the energy. Let me just write it here, and we'll get on with the correction to the eigenstate. Now we are gonna consider that L is not equal to M to find the correction to the eigenstates. Now just notice, like just as we did with the, well, let me just rewrite this. Just like we did with the previous case, with the first order correction, when we make L equals to M, we get that Cn doesn't appear in our equation, so we cannot really determine it. So again, I have just put the second order correction, the nth component being equal to a question mark. We don't know what it is yet. We'll do it in the next video, maybe. So if L is not equal to n, then we have this. Well, of course, we can group these two terms together. And we can just write EL0 minus EN0 CL2 plus this. Okay, we have just grouped these two together. We get first a correction, okay, to the energy, and this. And this just becomes 0 because L is different from N and they are orthonormal again, so this is just 0. So this is our expression. Yes, we can now just take this to the other side and isolate Cl2, and we would get that Cl2 is equal to minus this, okay, over EL0 minus EN0. Again, if we plug this minus sign here, we can just invert the order. Plus the first order correction to the energy as this inner product. Over EL minus EN0. If we multiply it by minus sign here and here, we get a plus sign, okay, it's just the same. we can distribute this minus sign here and change again the order. And the reason I change the order is just but it is more comfortable to always have En minus El just for us to remember, instead of sometimes having El minus En and so on. And this holds for all L different from N, okay, because we're taking Cl is not equal to N. And just notice that we said before this just picks out the Cl component of this, so we can just write this Cl component. And this will be our expression for Cl2. And we can do a bit better, right? We can kind of expand it and obtain a massive expression. And we're going to do it. Yes, let's just do it. So what we get, if we expand this term, is just, well, let me just write it like this. HP, and this is being applied to the sum over n different from n. Okay, we are just taking this expression that we derived before. M0 HP N0 over En minus El. So M times this. And all of this is over En minus El. Okay? So now don't get confused. This M right here is just a dummy variable for the sum, and this L is in general not equal to M, okay? They are two different things. This is just a summation, this M right here is just a summation, and this L is just a component of this. So in the end we will have two summations, but we'll see later on how. So all we have done here is just to expand this expression. I know it can be a bit confusing, right, having so many sub-indexes, but you just have to keep in mind what each index is. N, it is just telling us which energy we're correcting. L just tells us the component of the second order correction. And M is, we can call it whatever we want, it is just inside the sum, so it's just a dummy variable, dummy index. Now, minus En1, yeah, let's just expand this. The En1, we just get our usual expression, HP N0. N0 times Cl1, well, Cl1 is just all of this. So we can just write L instead, 0 HP by N0 over En minus, sorry, this should be an M, okay, I don't know, I wrote it wrong, it's an M, okay, don't get confused with it. En minus En. It's really easy to get kind of confused or to put a letter or whatever. So this would be the energy, Cl, and we just have to divide by, I'm sorry, this should not be an N, but rather an L, because we're taking Cl. Just change the M with the L's. I know the indexes can be really confusing though. En0 minus El0. Now, this would be our expression. We can simplify it a little bit. And let me just write it here. So in general, for L is not equal to N, we will get that Cl2 is just, well, taking this inside, we cannot really group anything else. We can just take this inner product here and just rewrite it, because L is in general different from L. So M is different from L also. So M not equal to N, we just get this term, or original term, over this difference of energies times this inner product with this one over En minus Al. minus, you see this expression are already starting to get a bit quite long, but well, this times this, so we just get N0 HP L0 HP N0 over, well, we can group these two together, they are the same, En minus El, so En0 minus El0 squared. So this expression is our coefficients for the second order correction to the wave function for L is not equal to N. Now in this case, when we will do in the next video normalization, we will find that Cn, right, the term that is missing here, is not zero. It also adds another term, so in the end we will have the sum over all of this, plus another term. So this is why I'm just going to be doing up to second order, because expressions just get extremely messy. I am going to write it for you right here, and we'll write in the end the conclusion. But you see that it's quite a bit messy. Oh well. So let me just write this here, and we'll continue with the normalization constants.